Hey everybody, this is a little bit of an addendum to the previous video. I'm going to call it 0.4.15.20 continued. I mentioned the previous problem was not a binomial distribution by any means, but it was a distribution of probabilities called a geometric distribution, which simply implies that the distribution is infinite. Instead of starting and stopping at values like a binomial distribution does, it starts at a value and then runs off to infinity, essentially. Now, of course, the likelihoods as you go off to infinity become increasingly small. Just like if you think about flipping a coin, I mean, what's the chance it's going to take you 100 flips until you see heads? Probably essentially zero. Although it can happen. You could flip 100 or 99 tails in a row and then flip heads. So it can happen, it's just not likely to happen. But what I wanted to show you was that mathematically you can demonstrate that the sum of those sequential probabilities that get harder and harder and to see actually do sum to 1. So here's just some of your probabilities in that chart from the previous one. It started at 0.4, then it was 0.6 times 0.4, 0.6 squared times 0.4, and so forth. And I just made that be a general 0.4 times 0.6 to the nth power, where n is going off to infinity. So again, very abstract. If you don't like math and math proofs, you could probably turn this off right now, because this will not, you will not like this at all. There's a trick I learned in college, and that's probably a good indication right there that you might not like this, that you can sum infinite series like this by creating a second line. Now, this is just an equation. You know, this is equal to this. I'm going to multiply both sides of this equation by 0.6. To which most of you are going to say, why would you do that? And if you hang on for 1 second, I'll show you why I will. So I'm going to do this equals 0.6 to the 0.4 plus 0.4 times the 0.6 plus dot 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 0.4 times 0.6 to the n. And what you end up getting then is, if you distribute those 0.6's down there, you end up on this side with, and I'm going to write this in blue, you get 0.6 times the sum of the probabilities that you want equals, now watch this, 0.4 times 0.6 plus 0.4, whoops, times 0.6 squared plus dot dot dot, I'm going to put 0.4 times 0.6 to the n plus 1. Now, why is this interesting? Why would we care about this? Well, if you notice, this term is the same as that term. This term is the same as that term. This term would be the one right before this one. So what we can do is, we can take the above distribution, I say distribution, I mean equation. Take this equation up here and subtract it from this equation down here. So watch this. Sum of the p of x's. Write that down again down here. 0.4 plus 0.4 times 0.6 plus dot 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 plus 0.4 times 0.6 to the n. And if we subtract that whole thing from this whole thing up here, you'll notice what you end up getting. Oh, excuse me. Put it the other way around. We're going to get negative 0.4 sum of p of x. Okay, don't worry about that negative. We'll deal with it in a second. Equals, now, this is going to cancel that. This will cancel whatever next to it. Lots and lots and lots of things cancel, 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 cancel. And then at the end, you're going to have this negative 0.4 here. And you're going to have a positive 0.4 times 0.06 to the n plus 1. Good so far? All right. So now, what you end up seeing here is you end up seeing quite a bit of 0.04, 0.04, 0.04. I'm going to make math a little bit easier for us by taking the opposites of all of that, making it equal to that. Now here's where you're going to have to think mathematically a little bit more than usual. Okay? Since there's a 0.4 here and a 0.4 here and a 0.3 here, I can divide through by all those 0.4s, and I end up with just the sum of the probabilities of x equal 1 minus oh, I got an extra 0 in here, I apologize. That should be 0.6. 0.6 to the n plus 1. Now here's where you have to think calculus a little bit. We're trying to show the sum of the probabilities equals 100% or 1. I think we're almost there. If that's true, that means this piece right here has to be 0. Well, think about it. If n is infinite, if n goes off to infinity, it stands to reason that this term has to be 0 because it's shooting off to infinity. So since it's 0, we are left with what we were trying to show, which is the sum of the probabilities equal 1. And you can see this argument only makes sense, and it only is believable if you indeed let the thing go off to infinity, which it actually does. So there you go. There's a neat little mathematical proof of why the geometric distribution probabilities sum to 100%.